In this video we're going to take a look at using the formal definition of an infinite limit by solving an example problem, which is one from the notes. If you're following along with those, that would be example 7.3.2. Okay, so what we've got here is we've got this definition of a limit which says that the limit of a function equals infinity if for each positive n there exists a corresponding delta. Okay, so you should always be thinking this delta is going to depend some way on n, such that our function is greater than n for x in the domain of the function within a small distance of a. Okay, a is the thing that the limit is going to. So for our example, what this means, I'll draw a quick sketch of what 1 over x squared looks like. Well, 1 over x squared, that's going to look a wee bit like this. Okay, so it's essentially something that goes off to infinity as x gets close to 0. Right, so let's just illustrate what our definition means for this example before we actually solve it. So we're saying that for every choice of n greater than 0, so let's choose one here. Here's my n. I need to find a delta such that my function is greater than n. Okay, so if we draw an imaginary line across here, such that my function is greater than n for anything less than delta away from my point A, which here is 0. So what this means is I'm trying to find a delta, okay, so a distance away from 0 I can go, such that the function is above n anywhere in that band. So again, we could draw that on the picture. Let's just say we chose delta to be here. So A is 0, so just drawing up here, notice that for anything in this band, for all values of x between delta and negative delta, the function is indeed above n, so that's all good. So when we actually want to use the definition to prove that this limit is infinity, we need to be able to find the delta that works for every possible n, and that delta is going to depend on n in some way, normally. Okay, so let's have a crack at doing our example. So we want to find, if we just translate the definition into our terms, want to find our delta such that the absolute value of x being less than delta implies 1 over x squared is greater than n. Okay, and I've slipped up here. I should also first state, okay, so a given an n greater than 0, we want to find a corresponding delta such that absolute value of x minus a, which is x minus 0 for us here, being less than delta implies 1 over x squared is greater than n. Okay, now often what you want to be able to do, you can often get the thing you want by rearranging the inequality here. So we're going to do that. So here we're going to note that 1 over x squared is positive, and so is n. So we can take a reciprocal of that inequality, and we'll get another inequality with the sign reversed. So hence we'll get x squared is less than 1 over n. Okay, and now we know that the square root of x squared is by definition absolute value of x, well, not by definition, but you know what I mean. Square root of x squared equals absolute value of x. So we can take the square root of both sides of this thing. It's not going to affect our inequality, and thus absolute value of x is less than 1 over root n. Okay, and that's the kind of thing we wanted. We've chosen an n, given an n greater than 0. We've found a number that depends on n, that the absolute value of x is less than. Okay, and that's come from saying that our function was greater than that value of n. So at this point we're basically done. Hence delta equals 1 over root n is a suitable choice. This is going to be true for all positive n, and hence the limit as x tends to 0 of 1 over x squared is infinity.